Okay. So, hi everyone, my name is Claire, and today I'm going to talk about sparse stochastic bandits. This is joint work with Vernade and Jun Kwon, both of them are here. Right, so as announced in the title, we are going to consider stochastic bandits problems with D sub-Gaussian arms, among which only S are good, that is, have a positive expected payoff. After T round, the regret rewrites as a weighted sum of the gaps over all the suboptimal arms of the problem. And our hope is that whenever the problem is sparse in some sense, the regret scales as S log T instead of the usual D log T. A question that arises naturally then is, what is sparsity? And whenever we have such a sparse problem, can we actually reach this big O of S log T performance instead of big O of D log T? So there's been some literature on the topic in online learning under sparsity assumption, under the full information setting. People looked at sparse reward vectors. And as far as bandit feedback is concerned, people they did some work on linear stochastic bandit problem with sparse parameter. Those two simultaneous submission to AI stats consider sparsity and like different kinds of sparsity with different kinds of regret guarantees in the end. But I will let the discussion of this topic to the dedicated page on the blog by Csaba Sepesvári and Tor Latimore at banditalx.com. So to start with, we get an idea of the characterization of sparsity by proving a problem-dependent asymptotic lower bound on the regrets. So this is a conditional statement. On one side, on one hand, the problem-dependent expression on the left, when this expression is positive, then we have a lower bound on the regret that is a sum over the S good arms of the problem of gap-related quantities. So this leaves hope for our regret to scale as S log T. On the contrary, whenever this expression is negative, then we recover the Lai-Robbins lower bound that scales as D log T, so then there is no hope for the problem to scale as the regret to scale as D log T. So maybe let me give you a hint of how we can characterize sparsity according to this result. So we extract two different kinds of sparsity. First, sparsity by scarcity, when the number of good arms, S, is much smaller than D. And we also have sparsity by domination, whenever the gap to optimality delta S is much smaller than the gap to sparsity mu S. But when it comes to solving this kind of problem, very originally, we supposed to run UCB, or rather UCB with a twist, that we call sparse UCB. So essentially, the goal is to run UCB on a set of S good arms. But to identify those good arms, we define a set J of T of S active arms at each from T. And this set is defined such that it takes only a finite number of pools in order to identify for good arms to become active. The main issue arises when whenever like one of the bad arms happens to be in the set of active arms, and when simultaneously the best arm is not in this set. Then it would take a very long time for the best arm to come back in the active set. So we add this force log phase over there in order to make sure that this bad event doesn't occur. So we show that the round-robin phases don't cost us more than a constant term, and that this force log phase actually is not more than a big O of S log T term. And if we add the big O of S log T term due to UCB on the set of active arms, then we get the regret scaling that we were looking for. So let me show you in practice like the empirical results of sparse UCB. So under scarcity, when when the problem is not sparse, then, well, sparse UCB behaves just as UCB. And when the number of S arms goes down, then sparse UCB performs better and almost reaches the asymptotic lower bound. And now if we play with delta S in order to have a problem like a sparsity by domination, well, when the problem is non-sparse, again, sparse UCB performs like worse than UCB because of, the additional pools that we added to exploit the structure of the problem. But when the problem is sparse, then we reach much better lower regrets. So in a nutshell, the main take-home message of this work is that we have a characterization of sparsity for stochastic bandit problems, and we managed to find a way of running UCB that makes use of the structure of the problem in a near-optimal fashion when the number of arms, of good arms S, is known. There are some remaining questions. Especially, maybe we could find a way of running UCB in a more maybe adaptive or more efficient manner. And also, it's still an open problem to know whether this prior knowledge of S is necessary or not in order to solve this kind of sparse problems. And we could also imagine to generalize this work to other forms of sparsity, maybe. So, well, thank you for your attention, and I'll be happy to meet you at the poster session tomorrow.
Questions? I don't have any as well. Oh, sorry, you have one, please.
So it seems to me that these bounds, they are not shift invariant. So if I shift the mean rewards by a constant, then the bounds are going to change, but the algorithm is probably going to still do the same thing. Do you have an explanation for this, or maybe I'm missing an assumption about the means?
I'm not sure. You mean if we could shift it as if the zero was like an arbitrary threshold?
I could just shift that mu I squared to infinity, all of them, and then that term just goes away.
If you shift, okay, it's. No, I'm not sure I get it.
Oh, you guys can feel free to take this offline.
Yeah, this is
Okay. Sorry. Yeah.